for the very kind intro, and it's mouthful. Thanks for covering them. And thanks all the organizer for inviting me for this wonderful opportunity to share my research with everyone. So make this window a little bit smaller, and then yeah, so if you have any question, please feel free to ask in the chat, and I may break in the middle to take questions for clarifications. Okay, so my talk today is generative models for structured distributional shift. So this is going to cover a line of work I have presented and studied in the past. And so you might have to hear pieces of this in different places, but I think today I want to present it from a particular angle, which is a structured distributional shift. So first of all, what is generative model? What do I know? What do I mean by generative model? So I'm sure we have all used the different kinds of generative AIs. I think behind the scene, there is a powerful engine, which basically can be represented as this kind of model. We collected a lot of training data, such as pictures of birds and dogs. They are sampled from some complicated high-dimensional distribution we don't know. And it's hard to represent it precisely, but we're able to learn this underlying distribution represented from some complicated neural networks. And then what this can give us is we can draw new samples. And these new samples are going to look similar, and this means statistically they follow the same distribution as the original training data. And so from this angle, we can view the generative model as a way to represent and learn high-dimensional distributions. But it is an implicit representation because we still don't know what the distribution looks like, but we can sample from it. Okay, so the mathematical angle I hope to talk about today is we can view generative model as a way to represent a structured shift of such high-dimensional distributions. So what do I mean is the following. Suppose there's some nominal distributions, and so this is dubbed as P. And so this can give us a structured shift family, which is going to be denoted by this Q is T push forward of the P. So this T is a operator. It is a mapping from D-dimensional to D-dimensional. Suppose D is the dimension of the data. And so this basically means that if we start from some P, we could shift the P to some other distribution Q. Okay, if I change the T, and I can introduce different distribution Q. So I call this a structured shift family induced by T with a nominal P as a reference measure. And so this T is going to be represented by the generative model. So I will argue that in many real world problems, this provides a tractable way to represent complicated distribution Q and using generative model to represent T. This can help us to solve the problems such as robust decision making, counterfactual generations. For example, we want to infer the counterfactual observations, which we cannot observe. And then finally, also uncertainty quantifications for complicated cases. So we'll start with the bread and butter for today, distribution representation and learning. Okay, so what are some typical ways to represent distributions? So I'm sure we all know, largely speaking, there are two ways. One is the parametric model, the other one is non-parametric model. In parametric model, we assume there is a family of distributions represented by some parameter theta. And we pick a family of distributions such as Gaussian, and then it's controlled by some parameter. And once we have data, we can estimate the parameter using methods such as maximum likelihood estimator. And this basically gives a family of distributions. And because we have already picked a function of the distribution, so this means the shape of the distribution is more or less fixed. For example, Gaussian gave us a unimodal distribution. You can shift and scale to create different shapes of distributions. So this has nice theoretical properties. We know MLE is asymptotically optimal, but this also imposes strong modeling assumption. For example, if the data is actually bimodal, but we fit using a Gaussian, this can create a model mismatch issue. So the non-parametric method can handle this better. It will let the data speak for itself, instead of imposing a shape start with. And so such methods includes kernel-based methods, smoothing spline, which are very popular in statistics, in OR, and so on. But they also face a challenge in high dimensions, so it has a curse of dimensionality. And so we're hoping that a generative model can be used in such cases where we want to have a flexible, non-parametric, quote unquote, way of representing distributions, but also can handle high dimensional data better. But at the same time, we hope that we don't just treat the generative model as a black box, but if we could retain some theoretical control of generative model as a component in our algorithm design. So to get a little deeper into generative model, and so here is a long list, I think, represents different kinds of generative models, all the way from the generative adversarial networks, again, which was quite popular, introduced in 2014 by Goodfellow et al. And there's many follow-up works. And there's also variational autoencoder, VAE, and also the more recently popular methods, including diffusion models based on score learning, and also the flow-based methods such as normalizing flow and many other extensions to make it more computationally efficient and performs better. So within this whole different kind of generative models, I think recently these diffusion and normalizing flow models are become popular, but all of them, I think largely speaking, can be described as a kind of model as the following. So largely speaking, these models are learning a giant or big neural network that can transform a sample from the noise into a sample, the following distribution of the data. And so on this side is the noise sample, for example, it follows multivariate normal with zero mean, identical with matrix, and the output is this X, which is T. T again is a neural network, and this transforms the noise sample and to represent a picture of the cat, for example. And so these different neural networks are different ways to represent this T and, to make it efficient. And so you can already probably see there's some resemblance of the distribution shift and the generative model if you represent it this way, right? So this, as you can imagine, the distribution of the noise is going to be very different from the real data. And so this transformation is also going to be complicated. So that's where we harvest the strong representation power of the neural network to achieve this task. By the way, this is a picture of my cat. So how to transform noise into a cat. So today's talk, I'll focus on the last type of model I mentioned, which is a flow model. And so mathematically, the diffusion model and the flow model are equivalent, but they have very different algorithm design and implementation. Why do I focus on flow? Because it has invertible structure, and this mapping is invertible. It also provides a clear connection with the transport map, and also explains the structure we need to induce the distribution shift. So that's why I focus on this. And mathematically, I also want to view the flow type of generative models as a flow in the probability space, okay, in a continuous fashion. It creates a trajectory of distributions. So I have two viewpoints to this. On the left-hand side is a particle space, which represent the data. And typically, we represent the movement we induced through the generative model in a continuous fashion, which is indexed by this fictitious time t. And so this is described by this kind of statistical mechanical way. We would say that the velocity field, which is the movement of the particle at time little t, is controlled by this velocity field. It is a mapping from RD to RD. D is the dimension of data. And so you can see this velocity field can change over the position where the data is currently located in the space, and also can be time varying. So intuitively, this basically describes that for each data point, we have a different direction and magnitude to move this data. This is controlled by the velocity field. And so as you can imagine, this data, they're sampled from some underlying distribution P. And so when we move the data this way, it will also change the underlying distribution. So we have an implicit way to handle or get a control of underlying distribution and drive it to move from some distribution P to distribution Q. So this one-to-one correspondence between the data and the inline distribution through the velocity field is a core principle behind the design. And so in the distribution space, if the distribution of the particles at time t following some rho t, and the distribution is going to follow the so-called continuity equation. So this basically is a conservation of mass. And so that means if you choose the control V in a certain way, it's going to drive the distribution to move in the, this basically is a manifold, move from P to Q. Okay, so the distributions is living on a manifold. Why manifold? Because as you can imagine, the distribution is not an arbitrary function. It has to be negative and has to integrate to 1. So we have to move along the geometry. Okay, so the next key concept I want to make more precise, as mentioned on the first slide, is this transport map. And so this transport map is coming from this definition of the Wasserstein distance for distributions. And so what is Wasserstein distance? It is a distance function defined between distributions. So if I give you two distributions P and Q, their distance is defined by the minimum transport cost. And so this is also called the transport distance sometimes. And so you can see, for example, if I pick the transport cost as the squared movement induced by T, right? So this is expected to the starting distribution P, and this transport map is act on the data itself, and the cost is this squared movement. And I also want to find this transport such that it will move the distribution from P to a target Q. Okay, so within all such transport map, satisfy the terminal conditions, the one that minimize the transport cost is the distance. Okay, and so as mentioned, there is this notation T sharp P. This is a transport map from distribution P to Q. This is the push forward operator. And essentially here, the key idea is we're going to use this T to represent distribution shift. Okay, so I put the causal here because later I will talk about the causal as well. Okay, so this is the transport map representation of this distance between distributions. So I'm sure some of you probably already seen this or familiar with the Wasserstein distance or Wasserstein metric. So largely speaking, I think two common definitions that are mathematically equivalent under some conditions are, one is the so-called Kantorovich definition of the Wasserstein, and this is defined as if you find the coupling, the joint distribution, that satisfy the marginal distributions and minimize the transport cost. So it's induced by this coupling distribution. And the Monge formulation is what I just described by this operator T. Okay, this is acting on the data instead of on, as represented through this coupling. And so these two definitions are equivalent if we have density, means that if the P has continuous distributions. Okay, so why do we choose the second one in my talk? Because I think it has a clear connection with the generative model. The generative model essentially is moving the data, and that's why I use the second representation. Okay, another question I want to clarify is here I talk about distribution shift through this transport map, and that has a connection with Wasserstein geometry, which is the transport map, transport distance between the distributions. There's another commonly used distance between distributions, which is Kalbach-Leibler or KL divergence. So why not use KL instead of Wasserstein? I think KL is also a very commonly used metric, and it has nice properties. And so a lot of fundamental results in the end becomes involving KL. But basically, KL definition is like you have to look at the ratio of the two distributions. In order for this to be well defined, I need P and Q to be absolutely continuous. This means that they share the same support. So essentially, if I consider P as this distribution, I can only induce Q a distribution as a redistributed mass, but the support on the same positions. So if they're both discrete, that means if P is discrete, that means Q also has to be discrete on the same support. And so because of that, I think, the Wasserstein sometimes in algorithms become more popular because it can measure distributions that has different support. Like if I have distribution support on this and the red one support on the different support, I can still measure them using Wasserstein, but I cannot measure using KL. Okay, so this induces a richer class of distributions. Okay, so now we have all the building blocks. Let's connect them together. Okay. And so I think the generative models, like I said, is give us a way to represent the T because this T is a RD to RD mapping. It is a functional, and typically it's not easy to make it tractable in practice. And so the generative model, especially full plate generative model, is basically, remember, we have this dynamic kind of equation to describe how we move the data. And this is from time t0 to t1, for example. If we discretize the time to many small time intervals, and then this is basically happens in numerical PD all the time, right? We can discretize time, and then we can integrate the velocity field over a small time interval. This will give us a small movement over the small time interval. And so this is precisely the idea of designing flow generative models, is you would take the velocity field and then you would integrate this over small time intervals. And this is going to be implemented using a RAS-block neural network in practice. And this V, velocity field, is going to be represented by RAS-block. And typically this is a shallow neural network with 2 to 3 hidden layers. And so then basically each of the RAS-block is inducing a small time movement. And then we design one block after another, and this will induce a change from some complicated distribution to start with into a noise, for example. And each of the RAS-block represented this way, and this represent V, will give a T that's invertible, because you can see, if I just give you an arbitrary T, it may not be invertible, but if I represent V by a neural network, then key inverse is just subtracting these displacements. So it's easy to make it invertible. And so that means I can build a mapping, this way, that I can map the data distribution, which is rows towards the noise, and I can also make it invert back. So this inversion part is important. That means I can take a sample in the noise space and map it back to the original data space. Okay, so this is the principle of the flow generative models. And okay, I have a little animation here. Let me try to make it work. So in practice, when we train this model, we have data, and data are particles given to us. So how we train this is we can map the problem as, for each time interval, we try to drive it towards the final target distribution. Suppose we have 3 data points to start with, and then at each given point, we try to say, let's move it towards the final target. And then this is an optimization problem we solve. Find a velocity field to drive it closer to the final target. And then you can solve this stage by stage, iteratively, and eventually converge to some target distribution such as Gaussian. So this is the particle-based implementation. Oh, sorry, I need to get back to this. So let me take 1 minute to fix this issue. And okay, share my slides again. Yep. Okay, where is it? One sec. Oh, I think I accidentally closed it. So let me just go back to my talk. Oh, okay. One more time. Okay, got it. Okay, so
you're not sharing the screen?
Yes, I will share now. Maybe this is the time to ask questions if there's any. Okay. All right, so I described this particle implementation, but let's I really unfold behind the scene what is happening here. Okay, like I said, I want to design a sequence of transport map. Each one is due to a small time interval, representing small time interval movement. And then essentially in the design, we want to find a sequence of the transport map that will drive towards this fixed target, which is my noise distribution, for example. And so how do I guide it? And so we use this kind of proximal, it turns out this is proximal descent in the probability space kind of formulation. And so this first term in my loss in each of the iterations is a KL distance between the final target Q, and then if I already at time K, I want to choose a T to move it further close to the Q. Okay, and so as you can see, this is the iteration. If I start with a initial distribution, and then I can, the flow of the process, I can move it to the next step, P1, and then I want to choose the T such that I can drive it closer to the target, and then closer and closer. So the first term in the loss is going to make sure we're always moving towards the final target distribution. And the second term in my loss is basically introduced as a Wasserstein 2 regularizer. And this will make sure that we're not making a too big of a step in our iterations. And this will ensure the algorithm has nice convergence properties and actually behaves stably. Okay, so as you can observe, actually, this kind of iteration look familiar. If you're familiar with optimization, in optimization, there is a type of algorithm vector space that's a proximal gradient descent, and it's used in a vector space all the time. And so it's a very similar type of idea that you want to minimize the loss, then you would try to minimize the loss, but with a regularizer, ensuring that in each step we're not moving too far away. And in a vector space, if you use the Wasserstein, if you use the Euclidean distance square as the regularizer, then you will recover the original gradient descent. So what we're having here is essentially we're constructing a similar type of proximal gradient descent, but where our object is in the probability space and it's represented through these transparent maps. And this kind of iteration actually, is very similar to something called the JKO iteration in this classic paper in numerical PDE. So essentially, this has a close connection with the JKO scheme. But in the original JKO paper, I think they show the convergence of this when you pass the limit when the time interval is tiny. And here we want to keep the time interval to be still discrete so we don't pass to the infinite. But we prove from a different route by viewing this as a proximal descent in probability space. And we can prove this kind of generation guarantee. And this basically says that we can achieve a good approximation to the target distribution if the number of iterations is on the order of log of 1 over epsilon. And so this is exponential convergence rate, which is a good convergence rate. It actually matched the lower bounds. And this E is the error. And so that's learning error capture many things, including neural network approximation because of these rest blocks. The finite sample effects because we have particles right, instead of population loss. The gradient descent errors and also inversion errors because when we do the inference or generation step, we have to invert these little transport maps. So if we control these errors to be on the same level epsilon, then we need to take big N iterations, which is log of 1 over epsilon. To achieve convergence. And so what this means in practice, this means that we can achieve a, neural network with a possibly small size. We all know that generative models typically is large. So with many, many blocks. So if we can make this big N small, that means we can use relatively small block, as small as possible to achieve our goal. So this basically is pushing to the limit to design this algorithm to be efficient. So it is reported in this paper with my co-authors and students. Okay, so this is, I think, the first message today, and I've, basically want to show that you can see we can induce a distribution shift. In this case, from the data to noise, it's a big gap, but in the exponential convergence rate, if we follow this kind of proximal gradient descent in probability space. Another extension I want to mention is this JKO step is nice, but in practice, computing the KL distance in the loss function can be hard in high dimensions. And I have shown this in my animation that you can see that if you simplify the KL, it's going to involve some term, and computing this term numerically may not be easy. And so the more recent trend is actually excuse me, replacing the KL by the so-called flow matching objective. And the idea is basically replacing this KL by a loss, it's a square type of loss, square loss. And so the idea is basically is you can show that instead of computing the KL in the distribution space, we could directly fit the velocity field. And so how do we do this? Again, if you have, for example, two distributions you want to match, and we have some particles from these distributions, then we can connect these two sides of the particles by some trajectory, and then essentially the instantaneous derivative of the trajectory will give us some velocity field. And we try to match this velocity field using, again, our neural networks. If you have many, many particles, asymptotically, this will recover. And so we take this idea of flow matching and we can also adapt it for this iterative scheme. And this is what we call the local flow matching. And similarly, we can also prove the convergence guarantee. But interesting, we find out with a similar type of rate, but the convergence guarantee in the proof, we have to assume stronger assumptions, and we have to change the distance measure to be chi-square in the final results. But this is going to give us a very computationally efficient, scalable algorithm. And here's some examples of generated images. And so I want to mention in generative model, this usually is the benchmark. Again, we have to show you can achieve certain FID, whether or not the generated images are going to look nice. And these pictures are 128 by 128, so it's 10 to the fifth dimensional, so it's pretty high dimensional. These pictures do not exist in real world, right? These are completely generated, and these are generated churches. And so this is the FID score, which is a typical metric to measure the quality of generated images. But I think they look pretty realistic. These are created by the flow matching type of approach. And so I also want to present this other example, which is we also tried this to simulate a stock data. And so it's a very, simple example. We take 6 stock returns, and these are SPY and others, right? So I take historical data and then using thousands of samples and using a relatively simple neural network with 2 layers of hidden layers and 3 stages of big N is 3. And then you can see basically, the blue one is the real data, this shows the distribution, and then the orange one is generated. You can see, roughly speaking, I think the generated data is matching the distribution of the real data. So this shows the capability and the flexibility of these generative models. Okay, so I think that finished the first part of the generation, but generation basically, I think, is most common task nowadays. And you want to induce the shift from data distribution to noise and also go back. But I think in many decision-making problems in real world, we wanted to induce distribution shift not towards noise, but towards something else. So that's, I think, what I want to cover next, which is the guided generation. I will cover 2 cases. One is for robustness. The other one is for counterfactual sampling. And so the first one is motivation is to design robust algorithm, a robust system, and as well zero learning, and also encounters problem a lot in operations research. For example, a lot of system we have supply chain, healthcare, patients monitoring, power system. We want our design of the system to withstand the worst case scenarios, right? So if the weather is bad, then can we make sure to minimize the power outages experience? So that means when we design the algorithms, we hope to test the algorithm to, not only to the training data we collected, but also to some synthetic worst case scenario, hopefully simulated or generated. And so because of that, I think a problem studied a lot, especially in the operations research domain, is the Wasserstein DRO problem. And so this problem is studying this minimax optimization problem, where the algorithm design or decision making is represented by the theta. And then you can see the differences in most of the algorithm design. You want to minimize respect to some loss. But in the distribution robust optimization problem, we want to minimize respect to the worst case distribution. And so this worst case is going to be represented by this Q. And this Q is basically a perturbed distribution from the nominal distribution. And this P could be our training data, could be our usual situations of operations, but we want to consider a Q that is perturbed from the P, possibly with some radius R. And the choice of this distance measure in many cases is Wasserstein 2, because of the reason like that, people believe this induces a rich class of distributions to test. So this can help us to build a more robust algorithm. And so there is a certain loss, right? So this loss could be, for example, classification errors. So that means we want to find a robust classification algorithm against the worst possible distribution within the vicinity. And many people have contributed to this topic, and I listed some of them. And I think one of the challenge here is actually to construct this Q, which is a distribution, possibly continuous and infinite dimensional. So this is not the usual vector space minimax, but it involves an infinite dimensional problem. And so because of that challenge, we thought about this way of representing the P using a transport map T, which we call the flow-based DRO. And so as you can imagine, the rest of the formulation is very similar to what we had before. And so we can write that minimax problem as an equivalent form in this way. And so you can see we bring that Wasserstein uncertainty set into equivalent using Lagrangian multipliers as part of the loss function. And so this is Wasserstein 2, for example, and this lambda is the regularizer or the amount of penalty we want to have to control the movement, right? And so then the minimax problem is going to be formulated with respect to this T. And in particular, I think in many problems, this L can be non-convex, non-concave. So in the existing work, a lot of times people consider the L being convex concave, then you can have strong duality. You can exchange the min and the max. But like I said, many decision problems, such even as classification, the loss is across entropy or logistic loss, it is not going to be convex concave. And so we want to cover that case as well. So we want to consider the L may not be convex concave. And moreover, we want to have a flexible choice of the lambda, which may not be a large penalty. So that means we can move a little bit further away from the P. And so if that happens, then this overall objective can be non-convex, non-concave. In that case, we cannot switch min and max. And so we consider two problems separately. And so this is covered in this paper, which is again with my collaborator and students. And so if in a case where the min and max cannot be exchanged, that leads to different problems. You can think about this as we call the stochastic Stackelberg game, because who plays it first will cause a difference. And so in this context, we want to show that can we find a solution of the theta and the t through some kind of minimax iteration. And in particular, we consider the gradient descent ascent algorithm, possibly with non-convex, non-concave structure and the general loss, general lambdas. And so I think the interesting thing here is we're able to prove a convergence guarantee to the stationary points with epsilon minus 2 iterations. Okay, so what happens here is there has been many nice work in the vector space optimization community to prove the minimax convergence of GDA. And so here the challenge is T is a functional. And so essentially we bridge this gap to establish this convergence guarantee. So that's the main message here. So again, bringing it back to what we can achieve using this, I have two examples to illustrate. So what this means. So this is a way to create, worst case scenarios. For example, the normal data, right? We collected is a dog, but then through this worst case generation, you perturb to the keel, then sample from the keel will look like a frog. You can see a little bit of this distortion or change of the pixels, and colors will make it look like a frog to a classifier. The classifier will make a mistake. So this will increase the loss. But then if you train the algorithm to be able to even recognize these pictures, it will make it more robust. And so another example is robust portfolio. So as I have shown in the previous example, we can simulate the stock returns. And so using that mechanism, we can further perturb it to the worst case distribution. And then we can do a portfolio optimization on top of these synthetic returns. And so this is a toy example, of course, but this illustrates the potential. And you can see this is a nominal, portfolio algorithm return and versus the worst case, the worst case design. And you can see somehow I think it achieves a better return, especially at the time horizon goals. So again, I think this shows the potential. Okay. And so I have covered the second case, which is how do we use this to induce a distribution shift? In the second case, it's shifting from a nominal distribution towards the worst case. And the next example I want to show is how do we use this for counterfactual sampling? I think with implication of causal inference. Okay, so what do we want to achieve here? I think it's also, we view this from a structured distribution shift point of view. Okay, so causal inference is becoming a foundational piece, cornerstone in modern machine learning, AI, and statistics. It has studied this a lot in the past. And so, for example, the core problem here is we want to tell the treatment effect, right? So, for example, we have a control groups, and also there's the treatment group, right? So we want to study whether or not this treatment is effective. So we want to compare the effect from the control versus the treatment. So this is average treatment effect estimation. And so, introduced studied a lot since Rubin, and it's a classic framework. And besides that, there's also conditional after treatment, average treatment effect estimation. So here we want to further introduce covariates and say that the treatment effect can vary over different features. And so basically, I think in these kind of treatment effect is you have this control cohort and the treatment cohort, and we want to take the average of their responses and to look at the average difference, right? So, and we're hoping that if we introduce enough randomization, then the average is going to give us a unbiased estimate and faithful. And so, but sometimes I think we want to go beyond average treatment effect estimation, but sometimes you want to achieve some kind of individual level counterfactual. And so I think this is closer to the principle of digital twin. So in those cases, sometimes we're interested in saying, of course, this is hard, not to say this is easy, but can we predict, for example, given what we have observed, right, for the same patient, and the patient is not treated, but can we predict what if you've treated this patient, right? And then what is going to be the outcome for this patient, very patient? And so in order to achieve or working towards this much more challenging individual sample level counterfactual, we have to be able to make a prediction for this individual patient instead of taking the average over the whole population. And so it's a very different setup and different problem. And so basically, I think this problem can be dubbed as if I gave you the covariates, and then given that we only observe one outcome, right? So which is, for example, control, can we predict the possible outcome for the alternative, for the counterfactual? So which is I dubbed as y hat 1 minus a. And so I think there's many motivation why you want to have individual counterfactual prediction. And so I think this problem was introduced by my medical collaborator, and they asked us, in ICU, they always face a quick decision how to treat the patient, what kind of IV injections to make. And so they can only treat the patient using one type of IV. But there's also the question, right? Maybe using a different IV will be more effective. But we can try this different treatment on this patient. So we have to make a prediction, right? So this is a very real problem. And also in policy evaluations, such as police patrolling, right? So we can only decide to patrol area or not patrolling area. So can we, based on only observation, and what we have so far, right? You only observe one possible outcome. Can we predict the counterfactual? So what we can achieve here, okay, so of course, I think this is a very challenging problem. What I'm presenting here, I think can only be viewed as a work in progress, and I don't claim we have solved the problem. But I think this could be my message here is I think generative model can be an interesting way to work towards this individual level counterfactual, right? So the challenge here is, I think a particular we have observational study only. It's not interventional, right? So it means that for the same individual, we can only observe one possible outcome. It's a missing data issue. We can only observe treatment or not treatment. And in order to make a prediction, we have to make more structured assumptions. So what I'm going to present here is if we can assume some structured causal model, and then also assume that underlying there is a shared representation between the treatment and untreated, then we can potentially make some individual level prediction. Okay, so in this case, the P and the Qs represent two distributions that are due to the treatment and control. Okay, so that's our P and the Q. And so this work I present here is, like I said, a work in progress. So we call the PO flow. It's a structured generative model for sample level counterfactual prediction, but under this shared noise structured model assumption. And so here we can possibly allow this multivariate outcome Y. But you can see we have the condition on the covariance and condition on one observation. So this has to be a conditional flow model. And right, so the caveat, okay, so I've already mentioned, basically it's not solving the complete causal problems, but this is going to give a prediction based on some assumption and the structure model. But let me highlight the idea. The key idea here is basically the following. So we have two distributions represent the untreated and the treated. And so they have different distributions, right? So each of the dot is one individual. But we're hoping that maybe if we can learn a mapping, right? This mapping is going to map it towards the noise. You can see this is the connection with generative model. We know how to do this mapping and with guarantee and efficiently. And then suppose we have mapped both P and Q towards noise, and the noise has no information, okay? So we can assume this is the shared latent between the treated and untreated, okay? So building this bridge is a key part. And then the idea is if we can learn this encoding and decoding function, which are our flow generative model, it is deterministic. The deterministic part is also important. That enables the inversion. Okay. And so in order to make an individual level counterfactual prediction, we can take one sample and use the encoder map it to the shared latent noise space, and then use the decoder to map it to the counterfactual domain that achieves the prediction. Okay. And so one natural question is, you would say, why does this make sense? When can they have the shared latent structure? I think we can provide some explanations, justify this from, I think, partially from some causal studies. And again, I don't claim this completely solved problem because causal is a, field require a lot of careful assumptions to make sense out of it. But I think this resembles a structured equation shared between the treated and untreated. So if the response is given by some underlying f that maps from the covariance, the treatment decision, and this u is basically representing the unobserved noise. And this noise can be represented through the noise in the shared latent in the generative model settings. So you can interpret this kind of shared latent structure in this counterfactual generative model as the unobserved noise in the causal structure models. Okay. And so, like I said, this can offer us some prediction under this assumption of shared latent. But besides that, I think the flow generative model also can give us likelihood, and this can be helpful sometimes to draw some inference. And it automatically gives us the Y that can be multivariate. So I think that's important in some context. And so what can we guarantee here? And there's an informal theorem statement. Basically, we can show that if, this is the important assumption. And besides, the usual kind of unconfoundedness and, and so unbiasedness. And so we can show that conditional X, right? So if the noise and the control, right, or decision of the treatment are independent from each other, then we can recover the shared latent noise under up to reparameterization. So this is the key step in achieving some kind of causal prediction. But I have to say this does not give us causal identification. That is a much more difficult problem. Okay, so how does this perform? We have tried it on some common benchmark data, but here I want to say that indeed, in causal treatment, in causal problems, especially counterfactual, there's no real world counterfactual because there's no way for us to treat and untreat the same individual at the same time. And so these benchmark data available are typically created under some kind of randomized designed experiments or some kind of simulation. People believe this is realistic. But so basically I've shown here this proposed methods compared to other benchmarks. Also some of them based on generative models, a lot of times have advantage. If not, it's not too far from the best. Okay. And one last thing I want to mention is we could also extend this idea. This previous, PO flow is for static setting where you want to predict the counterfactual. And we can also extend this for the dynamic setting with the DAC structure. And for example, the motivation is time series prediction. Right? So in this case, for example, we have time series 8-dimensional, but somehow we know there is a structure that one dimension actually will, creates things happens in another dimension. So this kind of DAC structure is very common in the Granger causal models. And so essentially we can understand like the prediction is like these variables, their past observations are going to determine the future observation in the other nodes. So essentially this so-called do flow we introduced to account for the DAG structure and also the temporal structure. Okay, so the main idea is in this representation, this generative model design, we can actually incorporate this kind of DAG structure, right, by creating the neural network connections and linkages to map this. Okay, and oh, by the way, I want to mention this is in this paper I think I mentioned earlier, this ICLR paper. So I mentioned two cases of shift, right? So one is worst case. The other one is counterfactual, where you want to shift the distribution from treated to the untreated or counterfactual domains, build a bridge between them. And the last piece I just want to briefly touch on is besides these two cases, this distributional shift viewpoint of generative model can also be used for uncertainty quantifications. So for example, in our recent paper, we have explored this for quantifying the uncertainty of prediction in time series. And so the motivation here is, a lot of times in time series prediction, we want to quantify the uncertainty. For example, you have this prediction, which is the blue one. And then we also want to have this shaded region tell us this is 95% confident, this is 98% confident, right? And so this can be done for statistical models such as autoregressive models, nicely analytically. But for a lot of the modern machine learning models, which are black box, right? So for example, attention, transformers. And so it's much more difficult to do this analytically. So what we can do here is basically we can learn some uncertainty models using, again, transponder maps. You can imagine in this case, I have a dynamic, I have an uncertainty set that changes over time, and I can learn a transponder map to shift my uncertainty a little bit, right? So that's the main idea here. And then from there, we can quantify the change in uncertainty set, and these represent, very flexible shaped uncertainty set. And so this is another illustration of the possible use. Okay, so I guess that's the end of my talk. Hopefully, I think the message here is a unified view that we can represent this kind of structured distribution shifts. And the structure is important, as you can see through these different cases. Then the P and the Q, what are the shifts we want to represent is different. Right? Generative model is a shift from the data to noise, which is a much more challenging case. We have to take many iterations. And sometimes P and Q are closer to each other than from noise to data. And then the transport map can be simpler. Maybe a few blocks of neural network is enough. But fundamentally, I think this transport map is a way we capture the shifted distribution, and then this T can be mapped to flow-based generative models. And I want to say flow is convenient, and it also delivers good performance because it's deterministic. But it is also possible to implement these using diffusion models, so not exclusive. And so I think there's a common mathematical language in here. As you can see in the handle of the theory, a lot of these problems can be written as optimization problem in probability space. Okay. And finally, I want to call it to, I think the causal part of this work still has a lot of work to establish the theory foundation of why this gives the causal prediction or counterfactual prediction. So yeah, that's finished my talk. Thanks a lot. And I would like to happy to take questions.